This research paper, titled Paper2Code, Automating Code Generation from Scientific Papers in Machine Learning, is authored by Minju Seo, Jinan Beck, Sungyun Lee, and Sungju Wang from KAIST and DeepAuto.ai. It addresses a significant challenge in the machine learning field: the scarcity of available code implementations for published papers. Only about 21.23% of papers accepted to top-tier machine learning conferences in 2024 include their code, which makes it difficult for researchers to reproduce results, validate findings, or build upon existing work. This lack of code leads to time-consuming and labor-intensive efforts, slowing down scientific progress. The paper introduces an innovative solution called PaperCoder, a multi-agent framework powered by large language models, or LLMs. These models are exceptionally good at understanding scientific documents and generating high-quality code, so the authors leverage them to automate the process of turning a machine learning paper into a fully functional code repository. PaperCoder mimics the workflow of human developers by breaking the task into three structured stages: planning, analysis, and generation. In the planning stage, the framework starts by creating a high-level roadmap. This involves outlining the overall structure of the project based on the paper's content. It then designs the system architecture, including generating diagrams to visualize how different components will interact. Next, it identifies file dependencies, meaning it figures out which files will need to reference or rely on others, and it generates necessary configuration files, like setup scripts or environment files, to ensure everything runs smoothly. Moving to the analysis stage, the focus shifts to interpreting the specific details from the paper that are crucial for implementation. This includes breaking down algorithms, understanding experimental setups, and clarifying any ambiguous parts of the methodology. Specialized agents within the LLM framework collaborate to extract and refine this information, making sure the implementation stays faithful to the original paper. Finally, in the generation stage, PaperCoder produces the actual code. This code is modular, meaning it's organized into reusable components, and it's dependency-aware, so it accounts for how different parts of the code interact. The result is a complete, executable code repository that researchers can use directly. To evaluate PaperCoder, the authors conducted both model-based and human evaluations. They tested it on various machine learning papers, comparing the generated code against ground truth repositories released by the original authors, if available. Human evaluations involved feedback from the paper's authors themselves, who assessed the accuracy and quality of the generated code. The results showed that PaperCoder creates high-quality, faithful implementations that closely match the intended research. Furthermore, PaperCoder was benchmarked against the recently released PaperBench dataset, where it outperformed strong baselines by significant margins. This demonstrates its effectiveness in handling real-world scenarios, even when starting from scratch without any pre-existing code, APIs, or supplementary materials. The paper highlights how LLMs are advancing beyond basic tasks, now capable of supporting end-to-end scientific workflows. By automating code generation, PaperCoder reduces the barriers to reproducibility in machine learning, potentially accelerating innovation. It emphasizes that while challenges like incomplete documentation in papers still exist, tools like this could make research more accessible and collaborative. In summary of the paper's contributions, PaperCoder represents a step forward in using multi-agent LLMs to bridge the gap between theoretical research and practical implementation, with promising implications for the future of machine learning development.